Hi everyone, in this video we are going to see Anna University's UG Engineering course with code MA 3251 Statistics and Numerical Methods, Unit 2 Design of Experiments. In this unit, we are given 4 major designs of experiment. The first one is Completely Randomized Design CRD, which is also known as one-way classification. And the second design is known as Randomized Block Design RBD, which in other terms can be called as two-way classification. The third one we will be seeing in this unit is Latin Square Design, which is also known as LSD. And the final experiment design in this unit is 2 square factorial design. The first design we will be going to our glance is on Completely Randomized Design CRD. CRD is the most simplest experimental design where treatments can be applied to experimental units by random process. Whenever the given experimental units forms as an homogeneous group, CRD can be applied. The advantages of considering completely randomized design is that CRD is easy to design and flexible to use. Also, the analysis of data is quite simple and straightforward. Further, for estimation of error variance, maximum number of degrees of freedom is allowed in CRD. The significance of one-way experimental design is that it permits any number of treatments and units per treatment. The major drawbacks of completely randomized design is that it works only with homogeneous set of experimental units. That is, whenever the experimental units given are heterogeneous, the experimental design becomes inherently less informative. Now, let's look into the working procedure of completely randomized design. In the first step, we set the hypothesis. We usually set the null hypothesis H0 as there is no significant difference between columns, and the alternate hypothesis H1 as there is significant difference between columns. From the given observations of the problem, we calculate their total and their sum of squares. In step 2, we write the number of observations n, the total number of all observations t. Using these two, we find the correction factor Cf, which will be equal to t square the whole divided by n. In step 3, we calculate the sum of squares. Firstly, we calculate total sum of squares, that is TSS, which is equal to summation x1 square plus summation x2 square plus summation x3 square plus etc. minus correction factor. Secondly, we calculate sum of squares between columns, that is SSC, which is equal to summation x1 square by n1 plus summation x2 square by n1 plus summation x3 square by n1 plus etc. minus correction factor. Note that here n1 is the number of elements in each column. And finally, we calculate error sum of squares, which is SSE, and is equal to the difference between total sum of square minus sum of square between columns. In step 4, we develop the ANOVA table. The ANOVA table consists of 6 columns, and they are source of variation, sum of squares, degrees of freedom, mean sum of squares, variance ratio f, and table value of f at level of significance alpha. The source is varied between columns and error. The sum of square between columns is SSC and error sum of square is SSE. The degrees of freedom allowed for columns and errors are respectively C-1 and N-C. The mean sum of square is the ratio of SSC divided by C minus 1, and mean sum of square for error is SSE divided by N minus C. To find the variance ratio, f should be always greater than 1. That is, if mean sum of square for columns greater than mean sum of square for error, then f is equal to MSE divided by MSE. Otherwise, f will be equal to MSE divided by MSC. To find table value of f at level of significance, we also compare MSC and MSE. If MSC greater than MSE, then table of FC will be looked for C minus 1, N minus C. Otherwise, table of F will be looked for N minus C, C minus 1. Here, the sum of SSC and SSE gives total sum of square, and N minus 1 is the degrees of freedom for total observations. In step 5, we write the conclusions. If calculate value of f is less than table value of f, we accept H0. That is, there is no significant difference between columns. Otherwise, if calculated value of f is greater than table value of f, we reject H0 and accept H1. That is, there is significant difference between columns. This is the working procedure for completely randomized design. In this way, we solve problems on CRD or one-way classification. The key thing to be always remembered while working completely randomized design is that the correction factor, total sum of square between columns, and error sum of square should always be positive, and the value of f should be always greater than 1. I hope that this video will be useful for you for understanding completely randomized design or one-way classification. I thank you all for watching this video. Once again, thank you all for watching. Thank you all for watching.